Now, but how about S device? S device actually today it will be more like EE128 class instead of usage of tooth. Yeah, because the usage is actually not easy, but however, you will also start from the template. Okay, so let's go to the, assume you have started the SWB, both of you.
Yeah.
Go to help and then training again.
Okay, we can close all the other tabs that we opened yesterday.
Yeah, you can close whatever you had before, but go to SWB. Let me know when you all open the help.
I have it open, but which section is it? Or...
now go to the Sentaurus Device.
Okay.
Yeah.
Okay, I'm here.
Yuan, you are okay?
Yeah.
Okay. Now it has basics, carrier transport. There are many things, a lot of things to learn, right? But you can do it yourself. But I will just take an example and then go over with you. So I won't go to the basics. I will just directly because I want to copy commands. So let me see what I should do now. I will go to the maybe carrier transport part, right? But here it doesn't have the commands. It actually has all the command here, so we can copy them. Let me search for one thing. It's not here. I try to, so don't worry. The reason I keep going back and forth because I don't want to copy and paste. I don't want to type anything wrong. Okay, so now imagine you are in the lab and you want to do measurement, right? Someone created a device for you. So you want to do measurement, but you are doing simulation, right? To do measurement, the first thing, right click, add a tool called S device, right? Can you do that? I will go fast. If you cannot follow, let me know, and then I show you again.
This is a new project, right?
No, the project you did yesterday with in which you already incorporated your device.
Okay.
Okay, so add a S device tool. Let me know when you are done.
Okay.
Right click, add, and then add a tool, S device.
Yeah, it's just slow for me. So.
It's just what?
It's just slow.
Okay, yeah. So let me know when both of you are done. Okay.
Okay.
If you have question, let me know also.
Okay.
Now, let's edit the master file. Right click.
Do we have to import any files before that?
No. I want you to edit the master file. Right click.
Yeah.
Edit.
Yeah.
And command. Right. Now you don't have anything. We are going to do this from scratch, and you probably do it only once in your whole life, right?
Okay.
You will work in this area. Okay. So this is the master file. It's blank, right? We can't do anything. So we don't have anything. The first thing is if someone gives you a device, asks you to do measurement, what will you do? You need to know where are the contacts, right? So there's something called electro section. Okay, so please type with me, electro. Right.
Okay.
In S device, mostly the syntax is between two curly braces, electro curly brace.
Okay.
Okay. And in this curly brace, we need to put the name of the electrode, right? I just type again curly brace, right, to be safe, and close them, and I put name equals to something. I don't put it yet. Voltage equals to 0. Now, what should I put? Well, if you are the one who designed the device, you know what you have, right? If not, let's say I forgot, I will open the file from yesterday, right? Open the MSH file. And then I look at it. Well, it has different electrode. It has string, gates, body, tie, source, or whatever, but they all in lowercase. I need to do the same thing. I want to put name equals to source equal to 0. And then I just repeat. I'm going to copy all of them. 1, 2, 3, 4. I will put string equal to 0. Body, tie equal to 0. Gate equal to 0. Substrate equals 0. This is just to initialize the electrode. Okay, so can you do what I'm doing now? Try to do this. And let me know when you are done, both of you. This is electrode, okay? Now, then another thing is actually sometimes I will mention this first in my training, is that actually I also need to tell something about the file. It's basically saying maybe which device you want to test, right? So yeah, you give me the electrode, but you do not tell me what are the files that I need to use, right? So here in particular, you will just copy with me. You will follow what I'm going to do. Copy first, and then I explain. Grid equals to, and actually I forgot all the command, and just hold on. I will need to pull up one of them as example, because I want to use the built-in variable, right? So here I go to just any of the project. You don't need to do it, you just know that I'm doing it, what I'm doing, where I find them. I just find the example, find their command, and then I know I need to copy this, right? I would like you to type it instead of copying it, and I'm going to explain to you. Under the file, you have 3, 4, 5 stuff, grid, and then I put at double quote, right? At TDR at plot, right? For parameter, let's don't do it now. I'm going to make a hash in front of it. What is the meaning of hash? Do you remember?
A comment, or like it's for SWB. So
yes, a comment for SWB. SWB, see the hash, and it doesn't know what is the meaning of hash space or hash parameter, then it treat it as a comment. It's going to ignore this one and not going to send to S device. Yeah. Okay. Now, so it has a few things. First is grid, basically is saying that which file you want to read. This one is going to get the file I explained to you last time already. The nearest file on the left, the tooth on its left that is nearest to it. And if I substitute with the file name, it is this one. If I press F9, then you probably will get n1_msh.tdr. Plot is that it's going to save. When you finish simulation, you're going to save a TDR file, right? Maybe I did not emphasize enough. The structure file we have been opening is called TDR file. It contains the structure information, mesh information, doping information, and everything. But in S device, after you've done the simulation, it's going to save a similar file. But here you contain the electron density distribution, electric field distribution, all the necessary content that you are interested in. So this is important. If you don't have this, it's not going to save, or it saves it as a name that you don't understand, right? But we want to save it. That's the great thing about TCAD. Current is to save something called PLT file. Last time we already tried to use S-Visual to open an IDVG, right? It is saved as a test file with the voltage and current relationship. This is what you can do in the lab. You go to the lab, you do measurement, you apply voltage, get the current. Output, it is just the log. So these are the standard thing, right? So you just copy all of them. Can you do that? And let me know when you are done. Okay, so these are the file, but still, right? You always, when you write a program, right, including using a tool, always imagine you are the computer. If I only give you this, you don't know what to simulate, right? Yeah, you give me the file, you tell me where's the electrode, right? You definitely need to tell me what you want to do. So here comes the so-called solve session. Right, so to do solve, again, this session, we will do curly brace. There are many curly braces, so try to do it in a pair before you put in more stuff, okay? So now I'm trying also to try an example. So what do I want to do, right? The first thing what I'm going to do is type this, couple, right? You just type with me, iterations. Look at this. This is not curly brace. This is the curve one, right? Equal to 100. And then I'm going to type Poisson. What does it mean? It means that at the beginning, please solve the Poisson equation only. Now, I have a device. I have this contact. At the beginning, I set the contact all to 0. So they are all 0 bias. There should be no current flowing, right? So I only ask to solve for Poisson. It will be easier because the current equation, the continuity equation, basically should have a constant Fermi level. So it is very easy to include them later. So I will first solve a Poisson equation and allow you to remember when I say it solve the Poisson equation, I wrote this complicated 3D equation to you before, right? It actually discretized into a matrix. And the goal is to solve it so that you get the phi for every mesh point, phi 1 all the way to phi n. Right? So how does it solve it? It uses a method called Newton's iteration. Right? I will explain a little bit more later. But if you use Newton's iteration, you cannot get the answer immediately. You need to iterate. But what if you does not reach the answer? Then it failed. You say fail convergence. So that's why at the initial step, we try to add more iteration because it starts with something, it doesn't have a good initial guess. So you keep iterating and iterating, and hopefully it comes to a solution. Okay, can you type this?
Yeah, I typed it.
Okay.
So when you say Newton's iteration, is it where it creates like a linear map, and as long as it gets closer to a solution, or like you know on a 2D plot where you take a point and then make it a line, and then wherever it crosses the x-axis is your approximate solution.
Exactly. I will explain a little bit. Yes.
Okay.
Yeah.
Yeah.
Okay. Now, so now let me explain a little bit what is the Poisson equation, what is the Newton iteration, right? You know, just like what you just said. For example, let us think about this, right? My goal is to find a solution A, this vector, right? AX equal to B. This is pretty complicated, right? But basically is to find out, I already know A, this is the differential equation. I know B, right? Remember I told you about this one. We discretize it into row, right? So the row is B, psi is X, right? This delta is A when you go into a matrix. Now this one is actually very computational intensive because it actually depends on n cube of multiplication, right? And you learn about Gaussian elimination to find this. But instead of doing this, all we can do is also to try to find out what is the solution of this one, ax minus b equals 0. So this is just like saying that, hey, can you find a function? I go back to one-dimensional. F of x equal to 0, right? So your f of x can be any value. Let me keep this. It may be something like this. This is the solution, right? So you have no idea where the solution is, right? So you have an initial guess. You say, hey, let me guess maybe the solution is x equal to 0. Then what do? You find the slope at this point, right? And then extend to here. So this is x0, the first guess. The second one, x1 equal to what? Obviously, you see that f of x0, right, divided by, if I call this delta x, equal to f dash of x0, right? So to find out delta x, we just need to evaluate f of x0 divided by f dash x0. So this is one iteration. It brings us to here. But then we say that, no, this is wrong. Why? Because now I substitute this one, I get f of x1, right? This is f of x0. It is not equal to 0. This is not a solution, right? If my curve is not that nice, let's say my curve is like this, then maybe I will just go back again to repeat it. Then this gives me x2. But I'm going further away, right? So this is not a nice curve, right? I did not draw a nice curve. So then this will diverge. After 100 iteration, you still cannot find an x that gives you f of x equal to 0. Okay, how about for this one? If I have a curve like this, maybe it will work. I start with this one. Do a slope here. It tells me that the next solution is here. So this is x0, x1. Then I come to here. Then it tells me that the slope is this one. Okay, it may give me this. Then this is very close to 0. Then as a result, I claim that, hey, this x2 is the solution because f of x2 is approximately equals to 0. That's the Newton's solution. Newton's method iteration, right? So when we say iteration equal 100, we say that we allow it to iterate for 100 times. After 100 times, you still cannot find the solution. I say it does not converge. The simulation failed. For example, if you are unlucky to have this curve, then you cannot find the solution, right? But usually you can find the solution. Is this clear to you?
Yeah.
Yeah.
Okay, good. Now, I want you to memorize this. Here, we have the so-called f of x. We try to make it to 0. This is on the right-hand side of the equation. How can you say someone when we achieve a solution? If you get exactly 0, right? If I find an x to give me exactly 0, then of course this is a solution by definition. So that's why when do you say that it converges? There are a few criteria. One is right-hand side is small, okay? And other is that when I'm moving this one, going left and right, when I'm very close to solution, you see going from x0 to x1, I have a very large delta x. Going from x1 to x2, I have a smaller delta x. And then in this region, the delta x becomes very small. In SD-wise, this delta x is called error. It's not really an error, but it just changed from one step to another step. We also say that if this is small, then we assume it converges. It means that you don't move much. Okay, so there are two convergence criteria you can use. One is the right-hand side is small, and other is the error is small. I'm going to show you the log file later, and then you know how to see that. Okay, any questions?
So are these, do you have to do both of these for convergence or just one?
You have the ability to choose both or one or
Okay.
each of them, yeah. But you want to be careful. Sometimes you can have very large RHS, but very small delta X or vice versa. So you need to be careful. But for you at this moment, actually, I don't expect my student to work with convergence because this is a very difficult topic. So don't worry too much as long as you have a typical setup. Okay.
Okay.
Okay. So then now so here tell you, although I spend a lot of time just for one statement, but then it applies to others. Okay. So after this one, we are going to type couple, right? You can also still put iteration to be large, but usually it converts very fast. It's done with the Poisson. Then we are going to introduce two equations: electron, and hole. So what does it mean? Now we are solving one more equation. Okay, that equation is, besides the Poisson equation, we also know that we have this continuity equation. If you remember, divergence of J has to be equal to the recombination minus the generation rate, where J equals to the Q, right? Mu and divergence of the quasi-Fermi level. I'm not going to spend too much time on this. This one is just like equivalent to the drift force, right, due to electric field, plus the gradient, the diffusion of the diffusion due to the gradient of the electron, right? If you really do research in the future, you're interested, we can discuss a little bit more how the electric field, which is the d phi dt dx, right? And this term through Einstein relationship convert to so-called quasi-Fermi level. So this is not electric field, this is just quasi-Fermi level, right? And you see that they couple with each other because you see here, I have the potential inside this continuity equation, and potential is here. Here, not potential, and potential is here. Here I have the charge, and here I have the electron charge, which is N. This charge is not just electron, it's equal to whole P minus electron. You also have the donor ionized charge and also the acceptor ionized charge. In some more complicated system, you even have piezoelectric charge, whatever, right? All the physics are taken into account. But what I'm trying to say here is, after only solving for Poisson equation, now it solve all of them at the same time to get the stable solution. Is that okay?
Yeah.
Okay. Now, so after this, we are doing this thing, right? A little bit complicated. I still want you to copy. This is called ramping now. Now you tell the computer you solve it. Please do quasi-stationary. Okay, let's just copy it with the brace. Initial step equal to 0.01. Right? Minimum mean step equal to 1e minus 5. Max step equals to 1. And then go, right? If you have a better programming skill or habit than me, you probably have better indentation, right? Be careful for all these curly braces. String voltage equals to 0.1. Okay, and after this, I have this curly brace again, couple Poisson electron. Oh. Okay. Maybe you copy it. When you're done, let me know, and then I explain. Okay, so let me tell you what we are doing. Imagine in the lab, when you are doing measurement, what do you really do? You apply a voltage, right? Based on this, I guess you know what it is trying to do, right? That's why Tuyen was saying that there's a typo, right? I try to apply 0.1 volt to the drain voltage. Okay, now, but how do I apply it? You said ram it to 0.1 volt. Because I start with 0, so definitely the drain voltage, if this is VD, my goal is that it was at 0. Eventually, I want it to reach 0.1 volt. That is my goal. Okay. Now I tell you how to do it. So in S device, there is a concept called time, T. But this time you have to be careful. In reality, you do have time, right? You say at 0 second, it was 0 volt. At 1 second, it becomes 0.1 volt because you tweak your equipment. So it ran in that way, right? It's up to you. Can say at 100 seconds later, it becomes 0.1 volt. That's all okay, right? But here it has something called time. When you see quasi-stationary, this time is not the real time. It basically is just a parameter. It say you go from 0 to 1. It only go from 0 to 1. So on the x-axis, this is 0 and this is 1. And basically what it does is that, okay, your goal is from 0 to 0.1 volt, right? Then at 0, you have at 0. At 1, I want you to ramp it to 0.1 volt. Okay, so can you tell me when the so-called time, which is just a parameter at 0.5, right? It's not second, just 0.5. What is the VD?
0.05?
Yes, as simple as this, 0.05 volt. So this is the so-called concept. But why I need to tell you this is because you see that it won't go to 0.1 immediately because you just ask the S device to, hey, solve the system equation when it is at 0 volt. You spend a lot of time solve it. Hey, here is the result. And then you suddenly say that, how about the solution when drain is 0.1? It will be very difficult to predict. So what it try to do is it try to increase the time gradually. For example, increase a little bit. How much? It will start with 0.01. Okay, the time, the t equals 0.01. Then what does it mean? It will try to have what should be the voltage when it is 0.01, when t equals 0.01. Any idea?
And 1/100th of 0.1?
0.01, right? Because it's 10 times less, right? So 1 millivolt. Correct? So it will start with 1 millivolt first. 1 millivolt is pretty close to the zero bias, so it will be easier to get the solution. Okay, so that's what it will do. Time at 0, right? Time, voltage, and step. Okay, start at time equals 0, my voltage is 0. Okay, then I'm going to have a step equals 0.01. Then that's why you go to the time equal to 0.01. At this time, you just told me this is the voltage is going to apply, right? Well, what if it converge very well? If it converge very well, then it looks a little bit wasting if I continue to have a step that is 0.01, right? So here, actually, I am going to add something called increment. I did not put here, but I'm going to put it later. increment equal to 2. Then say, hey, this one converged really well. We should not waste the time. How about let's do 0.02 step. I multiply this by 2. So this one will become 0.03 because I need to add 0.02. So now the voltage is 0.03, 0.03. Well, maybe it still converge very well. Then we say, hey, more, right? Then this becomes 0.07. Then this becomes 0.07. And maybe it's still very good. Then I increment by 2 becomes 0.08. Then now it becomes 0.15. Do you see that? I can go from 0.01 to 0.15 in 4 steps. If I did not have the increment, you will still be at 0.04. Very slow. You take a long time to reach 1. Make sense to you, this one?
Yeah.
Yeah.
Good. Yeah, very good. Right? Now, let's say I'm too aggressive. Maybe you say, hey, 0.05, now the step is too large. It cannot converge. Or it is struggling. It almost failed convergence. Then maybe now, let's say it does not converge. Then say, oh, I better cut back. Okay, this failed. Then let me cut it. I am going to have a decrement equals to 2, right? You can tweak this parameter. Then it becomes 0.04 again. Then it means this time I add 0.04 to 0.07, right? Because this one failed. So we don't have the result. We need to step back. We only have this point. So 0.04 add to 0.07 becomes 0.11, right? So then I'm going to simulate this one, 0.11. And then maybe this time is okay. It's not super good, but it does not fail. Then it will continue to use 0.04. Then now I go to 0.15 again. This time, because I have a good gas solution, so maybe I converge, right? And then I can continue. And maybe it suddenly converge very well. Then I'm going to double again. And that's how it do the simulation. Now, let's say it converge really well. Then what would you get if you plot the curve? You have a point here, 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 right? Because this going up exponentially. Then your curve will be something like this. Very coarse, right? I actually want to have a smooth curve. I want to have more points. Or I feel that I don't like to have this big step. So you can limit it. You say maximum step equals to, for example, 0.08. Then it's not going to increase anymore. You will just add 0.08 each time. Okay? If this one, let's say this one failed, you cut it back. You say, this time let me add 0.04, but still fail. Then you cut again. You say, okay, let me do 0.02. So it now becomes 0.09, right? Because I was 0.07. I add 0.08, it doesn't converge. Then I add 0.04, it doesn't converge. Then I 0.02, it doesn't converge for 0.09. Also, then I keep cutting. Eventually, you will cut to a point, let's say maybe 1e minus 5. It still does not converge. Then you will say, just say this is fail. We need to fix it. That's the fail of convergence. Okay, is this clear?
Yeah.
Okay. So in that case, let me continue. I mean, you will understand more later when you look at the log file, but this is some of the basics, right? So I told you I forgot to add decrement. It's up to you. They have a built-in default, which is 1.3, I guess. And then increment equal to 2. I do the same thing. You see the minimum step is 1e minus 5. It means if you reach 1e minus 5, you fail convergence. Okay, so just now what I told you is the quasi-stationary. What is the meaning of quasi-stationary? Basically, it says that you bias it at 0 volt. You wait for infinite amount of time. You go to steady state and you measure the current. Because everything is transient in our real world, right? We call it transient. So So each of these is a steady state, okay? You can also do a transient simulation. Now let's try what I'm doing here. I say initial step equals 0.01. I do the same thing, right? Minimum step equal to 1e minus 5. But I also need to give one thing called initial time, because now you're really talking about the time. It's a transient, same as real world, right? And so you also need to call the final time. Is here saying that I ramp this from 1 second to 2 seconds. But what I'm ramping, the same, I'm going to copy this one. Instead of ramping the drain, this time I'm going to ramp the gate. So my drain is already at 0.1 volt. Now I have to ramp the gate to 1 volt. Okay, and then the rest are the same. Okay, can you copy this and take a look, try to understand everything, and let me know if you have questions. Think about this. For example, when I try to bias a transistor, I put 0.1 volt here. I have to ramp it from 0 to 0.1 volt, right? It cannot be 0.1 volt before. Then you always, if you look at the drain current, you always take finite time to settle. Even this time can be very short, maybe 1 picosecond or 1 nanosecond. Still, this is the real case. But when you do this simulation, it reports to you saying that this is the current when VD equal to 0.1 volt. This is the current. Which current is talking about? It's talking about when this is a steady state, infinity, time equal to infinity. It's not taking this point. Okay, so basically it does not simulate this part. You just ignore the time and get the final result. But when I'm using transient, that is different. It is giving me the gate voltage at certain time. And that depends on how fast I ramp the gate voltage. Okay?
Okay.
So let me know when you're done.
Yeah, I'm done.
Yeah, I'm done.
Okay, thank you. Okay, so we have done this, right? Actually, with this now, this is the same. Everything is the same, except that now the T is the real T. You don't have to go from 0 to 1. This can be 1 to 2 to 2. Or you say, I want to run it slowly, 1 to 11. Still run the gates from 0 to 1, right? But you take longer time. I can also ram it, let's say, in 1 picosecond. Okay, and I need to be very careful. Maybe this one start from 0, right? Now, I'm giving you something called a very easy way of doing transient. You need to be careful when you try to mix quasi-stationary and transient. So I hope that you don't do this in your future research. Be careful when you try this, right? Just note that I know that this one is going to start from 1 and 2, because actually I don't know. I don't know whether this will start from 0 or what. So I just give a number, right? So for now, I introduced the transient, but I actually would like to keep this as quasi-stationary. But let's just do this, okay? Now, with this one, let's run the simulation, okay? So you won't get anything good, but you will get something. Let me run it. Run the simulation, see if we will get it through. I have error, right? How about this? You look at me and try to debug with me. This is the problem. First of all, it tells me that I have an authentic input. S device is very bad in reporting error. Almost all error is like this sentence. And also, it might not be 923. But however, be very careful. It says that in PP2, I have problem in 923. So I should actually open PP2, double click. And then I go to 923. Here you show me the line number 20, right? And then 23 is here. So I have problem here, right? I do not see what problem I have, right? I have this open curly brace and also this one, right? But before that now, this is 23, right? I want to show you, what if you open the master file? This is the let me see. Where's the one? Let me open the master file again. I go to 23. Do you see that? This is 24. Do you know why I have different number? Master file is 24. PP2 is same line, is 23. Any idea?
Is it because of the comment?
Exactly. Because we had a comment. When you go to preprocess file, the comment is gone. That's why it becomes 23. Right? So this is the first thing. When you see error, always look at the preprocess file. Do not look at the master file. Okay? Now, then I'm trying to debug. And I can tell you, it just tell you something wrong. Now I find that I have spelling error. Quasi-stationary. I missed this one. Quasi-stationary. Okay? Correct? Let's say I'm correct. I save it. Okay, I'm very happy. Let me run one more time. Now you see two things, right? One is not offending error. It's just a spelling error, right? But at least it tells me the right line, 23. Now I run one more time. Well, same error, what happened, right? Let me double click. Must be something wrong. Okay, it asked me to reload. Hey, how come it's still quasi-stationary? Didn't I change it already? Any idea?
Maybe you not save.
I save it. You're almost there. I save it. I did save PP2.
Maybe the pre-processed file, it's still processing the same one as before.
Exactly. So this is the problem, very troublesome, right? So I see PP23. I need to go to the pre-process file to find the error, but I need to modify in the master file because every time you pre-process, it just rewrite the pre-process file, right? It is based on the master file. Stationary, okay? Quasi-stationary. This time, let me try one more, try again, right? Hopefully it will work. Still have problem, but at least this time goes to 927. It means I fixed the previous error. So I go to PP2, I need to reload because as you said, right? It rewrote this one already. What is 27? This is 27. Let me see. Transient initial step equal to this, minimum step, initial time, final.
Transient one?
Okay, yeah, I did not realize that. Again, spelling, right? So that's why it's good to copy from template. Usually you don't type it, but sometimes you modify something, you will get into same problem. Okay, so let me try one more time. Double click. This time it gone through, right? But the problem is, how come it say that a recognized keyword decrement? Again, it is spelling, right? Decrement, this one, you give a better decrement, right? Should be MENT, okay? So this, if you are not familiar with this tool and you are in rush, you probably will spend a lot of time just to figure out. So the best is to copy from templates. Okay, I hope this time it will work. Yeah, now it is running, right? So can you do the same thing, try to run it? If you have error, try to fix it. If you can spend some time to look at the log file to understand what it is doing, and that would be exactly what I told you. You need the log file to verify what you have done is correct and also to debug, most importantly. Remember, our first task is to solve the Poisson equation. So the first thing is that I start solve the next problem, Poisson. Basically, it's talking about this line. Okay, now, so you start to do iteration. Remember, I say error is the delta x. You guess a x, and then you use Newton method. Of course, this is high dimension. It's not one dimension, but it still has a gradient, right? What we call Jacobian to find out the slope. And then you guess the next set of x. X is a vector now because it has, let's say, 1,000 points, right? It changed a lot, 1E5, okay? And the right-hand side is 3. It's actually looks small, but actually it's not small. It just say f of x equal to 3. It does not meet the criteria. Then you go to the next step. You see it is improved. Error is smaller. Still, it has a big jump, a big change of x, but the RHS is smaller, right? If it converges well, we say that this type of problem is so-called quadratic, if I'm correct about the term, right? It just converges very fast. You see that it goes from 1E5 to 1E4, 1E3, almost 10 times, 1 orders of magnitude at every step. Imagine if it is convergent in like 1.6 to 1.2 E5 in one step. It's going to take 10,000 steps or 10,000 steps or 100,000 steps to reach 0, right? But now we only reach 4E minus 2 when it is 7. In S device, if your error is less than 1, then it is assumed to be converged. This error is a normalized error. I'm not going to tell you what it is about, right? Because you understand we have many points, we have different quantity, right? We have electron concentration, we have potential. They all normalize and eventually come up with an error. It's in the menu. But as long as it's less than 1, we say it is converged. We assume the solution is there. Again, what is error? It's the change of x. We don't know the solution, so we actually don't know the error, right? If I know the solution already, why do I need to solve it? So the error is the change of x. But at the same time, you also want to set up saying that the RHS should not be too large. You have an option by default, I think is 1E minus 5. So as long as yours is either less than 1E minus 5 or the error is smaller than 1, then it assumes it converges. You have an option to say that, oh, I want the error to be less than 1E 1, and then the RHS to be less than 1E minus 10. You have that option. We won't discuss this now, but that is how it converges. Once it converges, it tells you the simulation time, and then it tells you all this quantity. What are the voltages across it, and then what are the currents? Of course, at 0, you should have 0 current. You won't get 0 because this is a numerical simulation. You have numerical noise. Right? If someone show you 0, 0, 0 like this, you know they fake the data. Okay. Now, after that, we introduce 2 more equations and solve it. It's very easy to converge. Just one step, it converges already. Then you go to the next problem. Now the goal is to ramp the drain to 0.1. So remember, initial step is 0.01. That's why you compute from t equals 0 to 0.01. Well, very easy for it. Only 3 steps, it converge. And you definitely see that it start have some meaningful current. Not meaningful, actually still pretty noisy, but meaningful already. 7E minus 16, the drain current equals to the source current, negative, right? Converges very well. So you see that it tried to have a larger time step. We say that increment is 2, right? So I expect to be 0.03. So the difference is 2. But however, it's not perfect. It has SDY has an algorithm. This is not really perfect convergence. If you converge in the first or second step, it may give you 0.02. But here it cut a little bit, but still very large. Step is almost 0.02. Okay, and then you converge. So you keep going up, larger step, keep going up, right? And this is an easy problem. So it converged to 0.1 very fast. After that, it will start doing the so-called ramping of the gate, right? Start from 1 second. And again, convergence is good. This is an easy device. And you see that it start ramping the gate. Okay. And eventually it finish after it ramp everything. And then it check in the license. It doesn't need the license anymore. And then it is done. Okay. Any questions?
Yeah, so the quasi-stationary function, it looks at steady state when no voltages are applied at the gate, and then the transient is when you apply a voltage at the gate slowly.
No, nothing to do with gate or source or gate or drain. Quasi-stationary, you can apply gate also, but it is give you the solution when it is at steady state.
Okay.
Right?
Okay.
Transient means that you really follow the time. You has all those displacement current. If you ramp it fast, it has a lot of displacement current. You ramp it really slow. For example, if I put this as 2E9, the result should be the same as the quasi-stationary.
Oh, okay.
Yeah.
So the transient function is used when we're concerned about the starting stages, right?
Yeah, and the ramping rate when the
Okay.
time is important for us.
Oh, okay.
Yeah. For example, in this case, we are not doing any memory, right? This device can do memory simulation. You inject electron, then you need to use transient because you need to simulate for how many microseconds to see how the threshold voltage change. You cannot use steady state.
Okay.
Yeah.
Okay, got it.
Good. Okay, so if no more questions, then let's go one more step. Now, this is not complete. Life is not that easy. First of all, we did not really turn on any physics. SDY by default has okay, how about this? Let's look at the output file first, right? Can you right click, visualize, Sentaurus visual, and look at the PLT, open the S visual. Let's try to inspect how the curve looks like. We plot the gate voltage as the x-axis and then the drain current as the y-axis. And this is the gate voltage. Right? You see, very ugly, right? Because we have a very huge time step.
Wait, which is the file? Is it the TDR file?
PLT file.
Okay.
And if you don't know why, right, we put this file here, remember? And actually, we should take a look at the preprocess file. Look at the input file, PP. You see that it successfully preprocessed it. It said it's going to take N1 msh.tdr as the input. It's going to save N2ds.plt and also TDR, right? So when we right click, we do see there are two files that we can use. One is N2 PLT, another is N2 TDR. And now we open N2 PLT. Are you able to open?
Yeah, I opened it, but I just need to format the graph because I can't really see anything.
Yeah, so please plot gates to the X and then drain to the Y.
Oh, okay.
Let me know when. First of all, I feel this is very ugly, right? I really don't like it. What can we do? Why is so ugly? Because my time step is too coarse. I already told you there's a way to do that. What can I do to make it smoother?
To make it smoother, you add more points, right?
Yeah. How do you add more points or limit the size? Do you remember? Maybe you.
We had a max step.
Yes, max step. Now I go back to max step. Let's say I use 0.01. That will be very dense, right? It will take quite some time because it means it's going to take at least 100 simulation, right?
Okay.
So let me try that, or you can try that also. Now I make the max step equal to 0.01. And I want to see.
If we run it again, will it open another one or will it update on
You
the
don't
CM?
have to, yeah. So this is what I want to say. First of all, you don't have to reopen. You can use this update key or F5.
Oh, okay.
I don't know which one. F5, okay? And also you don't have to wait until you finish. When it is running, you can keep updating like this.
Okay.
Okay. So obviously this is taking a very long time. I don't like that. So I decided to change it to at least 5 times faster, 0.05. So only 20 steps, right? So I'm going to stop it. I think I did not tell you how to stop a job, right? You just click on it and then click on this stop run man, okay? After stop, I submit it again. Right. And then I just refresh, wait when it is ready. Now it's ramping the drain now, and then now it's ramping the gate. I keep pressing the refresh key. That's why it's updating.
So what did you set your max step as? 0.01?
0.05.
Okay.
0.01 is a little bit too long.
Okay. And did you change your initial time and final time?
No, I don't. I still keep the same final time.
Okay. So 1 to 2, right?
1 to 2. Yeah. So all I did is just to add max step equal to 0.05.
Okay. And if we save the file, the CMD file, it'll save it for the master file, right?
Yes, you need to make sure you modify in the master file sdevice_des.cmd.
Yeah, but if I'm already modifying the master file and I save it, it should be saved, right?
It's saved already, yes.
Okay.
And then try to run again.
Should I? Oh, do I have to change the pre-processed file again?
You don't have to. When you run it, then you will pre-process.
Okay.
Remember? Yeah.
Oh, yeah.
Look nicer, but we actually miss a lot of things because in SDevice, by default, it does not turn on any physics. So I would like to add another section called physics, again with curly braces, right? So what do I need to do? There are many keywords I'm not going to teach you here. For example, I can say the device temperature. By default, it's 300. So I also put 300 here. So it's not going to change my result. 300 means 300 Kelvin. Do not put 300K. I used to have a customer, they put 300K. They thought that they are doing 300 Kelvin and they get very strange results because 300K means 300,000 Kelvin. Okay, so put 300. Mobility is the most important thing. Here you don't have any mobility model turn on, right? So if I can just look at a typical setup here, it has the physics session. I'm going to copy, for example, the mobility is going to be doping dependent. It depends on the doping concentration. E-law mode. E-law mode is that when you press the electron against the gate oxide, you've got this surface roughness and also something called surface photon scattering. Your mobility will reduce. Okay, and also high field saturation. High field saturation is saying that under high electric field, your mobility will slow down. If you have learned this before, you know that it's not like general relativity saying that your speed cannot be faster than the speed of light. In the silicon, when your electron becomes faster, it has higher energy, then it has more chance to lose energy through something called optical photon scattering. When it's a quantum mechanical thing. When you have low energy, you don't lose energy through that way. When you get enough energy, then you lose faster. So the velocity will saturate. Okay, so high field saturation is one of the model that we need to turn on, right? There are many things, right? We will just use the template. But I just want to show you, right? Can you type this when you are done? Then rerun the simulation. But however, wait for it to finish. Do not refresh it. Okay, I wait for it to finish, and then I open the file again, but I use the same as visual window. I just want to compare them. Okay, so again, copy this statement, rerun it. After it finished, becomes blue, load it, do not refresh it, load to the same as visual, right? So I will show you, right? And then wait for you when you're done. You can copy now if you want. So I'm done. I right click, visualize, right? I still select the same PLT, but I say go to the same SWB_2. I open it. Then I have another file here. I propagate outer voltage to x-axis, drain, total current to the y-axis. I see much lower current. In terms of, I also see other effects, but the current is much lower because the mobility is not as high as before. Okay, try this. Remember, don't refresh it. Good, right? So I will refresh it, and then they combine the same curve. This is just a matter of visualization. Next time you can try different splits, but now 2 more sessions I need to introduce, but not we won't go into detail. Also, another is the math. Math is very important, especially when you're doing 3D. It determines whether it will converge or not. It also determines, for example, how you define the Newton iteration will work. For example, iterations. You have a global iteration, usually is 20. You can say, hey, 15. For example, if you put 1,000, what will happen? At a step that it does not converge, you will try 1,000 times. It's waste your time. So you want to make it small. But if you make it too small, what happens? It's almost going to converge, but then instead you say, oh, you reach the maximum iteration. You need to fail and then cut back the time step. So usually you want to choose a number that is good for your simulation. So in this case, I use 15. Default is 20, okay? And I will just copy from here to see what else I should put. Let me see if they have map here. Right? You see they have many things which you don't need to worry about. Some of them are obsolete even here, but I just put them to be here. But I want you to try one thing, right? To play the game is something called, you don't need to copy this, but can you try to copy this? Digits. Digits is going to determine how accurate you want to simulate. Basically, we use 5, right? Again, I don't go to details. This is related to the error. If I have a smaller digit, then it will converge easier. Even I have a big error, it will converge. But in the log file, it still need to be smaller than 1, but it is trying to scale the error, right? Default is 5. Can you put it into 1 and run it again? See what happens. All right, you can ignore the others. Just add digits equal to 1 and run it again.
And then after we run it, you want us to visualize it?
Yeah, if you are able to visualize, I'm actually very disappointed we are able actually. But let me visualize it. 。
Okay.
I was hoping something bad will happen, but it does not because this problem is too easy for convergence, right? So I try to plot gate voltage. First of all, I really hope that at least I want to see the result to be different because it should not be as accurate as before. Oh, I'm happy, right? In worst case, you can even get it not converge. I was hoping that it will not converge. You see, it gives a wrong solution. This is completely wrong, right? How can it reduce, right? But it still converge. Why? Because you look at that, it can converge easily because the digit is 1 now. Even it was 10,000 times less accurate than before, I also say it converge. But you see the right-hand side is very large. Do you see that? Every time it converge, yeah, error is less than 1, but right-hand side is 1 billion. Okay, so that's why you need to be careful. But however, again, I don't think you need to treat this too much, right? For all the students who play with me, work with me for 1 or even more years, they never need to play with this, even they are doing 3D. This is a tough problem, right? But I want you to be aware of this. Okay, so this is the math session. And we also talk about the physics session. And then finally, I want to talk about the plot session. If you right-click this one, visualize, and then look at the TDR, it saves the snapshot after the simulation. For example, it has the electrostatic potential. Well, right? You see this is at higher potential, and this is at lower potential. It also has the hole density, electron density. Well, if you took E128, you know that you always just look at the table or just equation. Here really show you what exactly going on. See this inversion layer, very high density of electron here, going from left to right. But that's not enough. But these are the basic things they save. Okay, so if you want to see more, what would you do? You will going to add a session called plot session. Now you realize that I just insert at any place I want. Now I can tell you that for all this session, the order doesn't matter. You just follow what you like, but usually we put solve at the end. Plot, what would I do? I would come here, just copy a template. See if I have something here. If no, I will just copy from one of the templates we had earlier. I just copied this whole plot session, right? You don't need to follow me. All I just showed you. See, now I'm copying more than, I'm copying a lot of stuff, right? I plot electron density, total current, plot it as a vector, right? So I will run it again. But this time I want to change back the digit to 5 because that was too ugly, the results. Okay. And then I run it again. And if you want to try, then you can copy from, just copy from any file. Here I copy from the single device example. Okay. And again, I don't need to reopen it. I can just refresh it when it finishes. It finished, blue, yellow already. Now I have many stuff, right? I can look at the total electron density. It shows me how the total current density, how the current changes, okay? I can also look at the band gap, okay? Now, or even conduction band. And remember what you learned in E122, we always draw the band structure. I'm going to do a horizontal plot. I'm cut Y, remember, cut Y, click on this one. I click here, this is the surface. I move it a little bit lower so that it's in the silicon. I maximize it. Then I click this icon, it's going to show me the band diagram. So this is the band diagram for this device when it is going from source to drain. This is the conduction band. This is the valence band. So I think this is a good exercise. So why don't you go ahead to try this, right? So again, go to the single device, application library, getting started as device, single device, right? You just right click this file to look at its master file, and then copy this procession to your device, to your input file, run it, open that file, and do some cuts like what I'm doing, play with that, okay? And when you are done, let me know.
Okay.
Good exercise. So what you will do is to do a horizontal cut, right? You click on this Y, right? Then you will cut along this line, and then you will show you a graph like this. And you can click on this, then you will show you the band diagram. And of course, you can choose to any quantity we want to plot. For example, electric field, band gap narrowing, conduction band, or whatever. Okay.
Okay.
I just want you to take a look, play with this. Don't need to go too deep. If you have question, let me know. Let's continue. Basically, it's very good. We have done our first S device simulation, and then we are not going to. Just one more step I want to let you know. Parameter file. This is very important. Now, you have all this, but it's using the default parameter. What if I want to change the parameter, right? So can you uncomment this one? Then it means that it's going to read a parameter file. So how do I get a parameter file? Of course, you can type from scratch. If not, then you can do copy and paste. And that is usually what I do. But first of all, I need to create a master file. So you right-click as device, add the input, parameter. This is the master file for parameter. I click on this. It has nothing. I say, let me just, I have two choices. Maybe I can start with the silicon one, but I don't want to do that. There's too many things. So I just create an empty one. Okay. I say, okay. Right. Then there's nothing, right? Are you okay? All of you reach this step?
Yeah.
Okay, good. Now, there's something I really want to tell you is if you go to command prompt, just go back to a command prompt where you open the SWB, okay? You can generate a default parameter file from the system. You type S device space dash lowercase r dash space dash capital P colon silicon. It's going to generate the parameter file for you. Okay. S device space dash R space dash capital P colon capital S and then silicon. And the whole word silicon. Enter. It generates, but it also saves in a file called models.pal. So I'm going to use gedit open models.pal. Okay. Then it pop up in here. Is this okay? Can let me know if you can reach this step. When you have done, let me know.
Can you show me the original command again?
Yeah.
Silicon and then.
Yeah. You need to be careful of the capitalization and also the space.
Okay.
Now, I will copy this session. Material, just only copy this block. Control C. And then go back to my sdevice.pal. Control V. I need to add one more closing curly brace because it's saying that this is the parameter for a material called silicon. Okay. but actually I don't want to do silicon. I want to change it to oxide. I copy just for the syntax. Okay. And I want to put this as a variable, EPS. Remember what is at? EPS at is a user-defined variable. You can put in SWB. Okay, so this is the syntax. You never have to memorize. You just copy, but also understand that it is like material to something and curly braces, and then inside you have different section. Epsilon is the one to talk about the dielectric constant, the permittivity. Okay, so I change it to oxide. Oxide permittivity is 3.9 by default. Okay, but I now want to make it as a variable. Okay, let me know if you have done with this.
Okay, so I opened the S-Device parameter file, and it says material equals silicon, and then it says it has a comment, like hashtag include something else. That's it. Do you just want me to change it?
Right, that's why I say copy this part only.
Okay.
This is what you're saying, right?
How do we open the models?
Yeah, this is models.par. Right?
Is that also in the edit input?
You say what?
Where did you get the models parameter?
After you type this command,
Oh,
right, and then you use gedit models.par to open it.
oh, I see it. I see it.
And I actually forgot to record.
We were plotting the same thing, right? Gate outer voltage and then drain total current.
Yes. Right. So we added these two very 3.9 and 33. And then try to plot them together. Right click. Gate, outer voltage, total current to the right. Okay. So it's, oh no, this is wrong. This is drain current, total current to the left. Okay. I go to curve, delete the gate total current. So with higher permittivity, I got higher current. Okay. Let me know if that works for you.
Okay.
You're done?
Not yet.
Okay. So again, I think I recorded this part already.
So we're plotting this new one against the old.
You don't need to. Just open both of them in a new SWB and plot them. We only want to compare both of them.
Okay.